Good day, everybody. We're Team 1125. I'm Manuel Lisondra, joined by Miles Angelo Sodejana and Eric Dominic Manginsay. We're from the University of Southern Mindanao in the Philippines, and for this year's SCUDEM challenge, we'll be tackling our approach to problem C, dog cannot catch. Problem overview. Fritz, a golden retriever, went viral on the internet for his endearing yet comical glimpse of his struggles with catching thrown food. The video unfolds through multiple scenes where his owner tosses various food items to Fritz, only to witness his earnest attempts to catch them in his mouth. Questions posed about the difficulty of the task, precision of the dog's brain in estimating head and eye orientation, and time needed to position the mouth correctly in order to catch the food. Our objectives are as follows. To get time required for Fritz to position his mouth correctly in response to the thrown item, explore some factors such as the type of food, the impact of air friction on catching different foods, and the throw's initial height. To estimate the precision of Fritz's head and eye orientation to best predict the location of the food, and to identify critical aspects of Fritz's perceptions and behaviors for successful catching.
For our model assumptions, we first assume that the object in motion is spherical for simplicity. Typically, for an object traveling through air, it undergoes quadratic drag, since linear air drag is only applicable for low-speed objects in viscous medium. So for our model, we assume that the food follows a projectile path with quadratic air drag. The initial velocity of the food is the same throughout all throws, and because the video showed that the food is thrown upward, we assume that the vertical velocity is greater than the horizontal velocity. For simplicity, we also assume that Fritz's initial distance from the thrower is the same throughout all throws. Next, his vertical velocity is 0 when he is stationary and constant when he jumps. Based on literatures, the height of a golden retriever from the ground to his head is 0.81 meters. So we estimate that his eyes are located 0.75 meters from the ground, 6 centimeters away from the top of his head. To avoid complexity in his head dynamics, Fritz's head and mouth follows the motion of his eyes. Consequently, Fritz's head, eyes, and mouth are assumed to have the same velocity. In developing our model, we consider two cases. Either Fritz would jump or would only move forward and backward when approaching the food, which leads us to our next assumptions. Case 1. Fritz opens his mouth and orients to the same initial Y position of his eyes or eye level, adjusting forward or backward at the time he catches the food. Case 2. Fritz opens his mouth and moves with a constant vertical velocity at a certain time tau upon jumping before he catches the food.
For our variables and constants, we have T sub catch, which is the time that Fritz catches the food. We also have tau, which is the time delay of Fritz's movement or the time when Fritz starts to jump. We have h sub f, which is the initial height where the food is thrown at time is equal to 0. We also have status of orientation, which is the angle of orientation of Fritz's eyes with respect to the trajectory of the food item. This variable is used to solve for the precision of Fritz in order to catch the food. Next, we have the mass of the food, which we denote as m, followed by the drag parameter, which we denote as b. Since we assume that the object is spherical, we follow the formula 1/4 rho a squared, where a is the area of the circle and rho is the density of the air given by 1.225 kg per cubic meter. We also have the acceleration due to gravity, and also h sub e, which is the height of Fritz's eyes with respect to the ground, which is estimated to be 0.75 since the height of a golden retriever is 0.81 meters based on literatures.
Our general model, which is shown in the current slide, is a first-order ordinary differential equation that represents the relative velocity of the food in motion with respect to Fritz, the golden retriever. It is derived by applying Newton's second law of motion. Again, there are two cases. For the first one, initially, Fritz is not yet jumping. Hence, the initial conditions shown are at time is equal to 0. The absolute x and y velocities of the food can be determined by these differential equations shown that follow Newton's second law of motion. Force is equal to mass times acceleration, where acceleration is known to be the derivative of velocity or the second derivative of position.
We also have the absolute velocity of Fritz, particularly the motion of his eyes, with the following boundary conditions, and then using the equations for the absolute velocity of Fritz and the food in the projectile, We derive the equation for relative velocity as shown. We then integrate it and get the relative coordinates of the projectile with respect to Fritz. Here, we added the term tau in the x-coordinate simply because we assumed that Fritz moves horizontally at certain time tau. For case 2, similar approach is used to derive the model, but it is only applicable at time tau, and then the motion of the food is now relative to his mouth instead of his eyes because that's the time his mouth moves to catch the food. Using the same methods, we arrive at the relative x and y coordinates of his mouth starting from the time tau as shown. We can use case 2 to model a more dynamic scenario where both Fritz's horizontal and vertical movements are taken into account, but due to lack of values for the time delay tau and Fritz's velocity, we focused more on case 1, where he opens his mouth and catches the food at a point where his eyes meet the projectile. Finally, here are the equations that we used for solving t sub catch for both case 1 and 2 by simply setting y bar to 0 and then use the formula for angle of orientation shown to determine how precisely he should orient his head at certain time t.
We estimate Fritz to be at a distance 1 to 2 meters from the thrower, and the food is thrown at a height between 1 and 1.2 meters. By assuming the initial velocities u sub x and u sub y to be 2.5 and 3 meters per second, as well as the other constants shown in the figure, we get the graphs for both the relative and absolute projectile of the food. In relative velocity, we set Fritz's eye to be approximately at 0.00. This is also the point where his mouth should be, assuming that he follows his eye and moves his mouth to that point at t sub catch. For the precision of his head and eyes, we use the equation for the angle of orientation in different values as shown in the figures. For initial height thrown and its angle, for the food diameter for air drag and its angle, and for the food mass and its angle. Using 2 points in the projectile for the basis parameters which have clear differences in coordinates, we pick the basis angles at critical point and at time 0.524 seconds to solve for the angle orientation. From the data we obtained, we see that both varying initial height thrown and drag parameter b affects the range of the projectile. The higher the initial height thrown, the greater the range, implying Fritz to move backward, and the lower the initial height thrown, the lower its range, implying Fritz to move forward. On the contrary, the greater the drag parameter b of the food item thrown, the lower its range, implying Fritz to move slightly forward, and the smaller the drag parameter b, the greater its range, implying Fritz to move backward. These angles can be used as a basis for Fritz to move forward and backward or just stay still or catch the food. To solve for the time that Fritz should catch the food, we use the equation shown, and with the aid of Wolfram alpha, we get the following values. In both parameters, initial height thrown and air drag, we see an increasing values of time for Fritz to catch the food. Given the range of values we set, we can see that changes in initial height thrown affects the projectile more than the air drag. We neglect the effect of mass since our range of values is approximately negligible. As for the case 2, we'll only briefly discuss Fritz's attempt to catch the food given the assumed values shown, noting that these are just mere assumptions. The angle of orientation is just the same for case 1, but for t sub catch, we use the formula to get the value 0.6657 seconds. If we increase and decrease tau, or the time Fritz to attempt to catch the food and jump, we see that if Fritz moves earlier, he'll have to jump higher, and if Fritz moves later, he'll have to jump lower. If he jumps too late, he'll have to catch the food jumping backward, which can be complicated.
The limitations of the model are as follows. First, the object in motion or the food is assumed to be spherical, therefore we did not take into account varying food shapes. Second, the dog's motion is only limited to whether he jumps vertically or move horizontally forward or backward. Combinations of those movements, for instance jumping vertically and moving backward or jumping vertically and moving forward, is not considered in our model. Third, the mouth's movement, opening or closing, is not integrated in the model.